Hi, I'm Marcus, a D4 student at the University of Oxford, and I'm pitching my research, the measurement of thermomechanical properties of nuclear graphites at elevated temperatures, as part of the Pitch Your Generation 4 research competition. Graphite is said to be used as the neutron moderator in both the very high temperature reactor and the molten salt reactor. Within the reactor core, the graphite is subject to elevated temperature, very high cumulative radiation doses, and thermally and mechanically induced strains, all of which drastically alter the graphite's thermomechanical properties, including its Young's modulus, tensile strength, and coefficient of thermal expansion. The purpose of my research is to investigate the fundamental mechanisms by which elevated temperature and irradiation change and alter the structure and properties of graphite at the nano and microscale, and relate those nano and microscale changes to the macroscale changes that we observe in graphite components. This will aid engineers making their structural integrity assessments and also aid researchers looking for the most suitable graphite grades for the Generation 4 reactors. So how does my research answer this central question? The first set of experiments I'm doing investigates the deformation mechanisms in graphite, specifically the effect of temperature and irradiation on kinking. Previous work has shown an increased propensity for kink formation in graphite at elevated temperature, which is shown in figure 1, where you can compare the much smaller kink region in image B at room temperature to image D at high temperature. I will use high temperature spherical nanoindentation on an ion-irradiated pyrolytic graphite and combine that with cross-sectional TEM imaging. This will allow us to relate the observations of the graphite deformation in the electron microscope to the measurements in the modulus made by the nanoindenter. We will be able to understand for the first time the effect of irradiation as well as temperature on this kinking mechanism. Deformation mechanisms in graphite are very important because they allow the material to relieve induced strains that would otherwise cause microcracking and eventually component failure. This leads me on to the second series of experiments I'm doing, where I'll combine X-ray radiography and X-ray diffraction at high temperature to investigate the relationship between bulk applied strain and induced crystal strain in a neutron irradiated fine-grained graphite. This will allow us to investigate how elevated temperature and neutron irradiation alter the ability of the graphite microstructure to accommodate induced strain, which is intrinsically linked to how elevated temperature and irradiation influence the deformation mechanisms in graphite. The third series of experiments I'll be doing investigates the differences in coefficient of thermal expansion between the two phases in polycrystalline graphite, the filler particles and the matrix, which are shown in the X-ray tomograph in figure 3. This is very important because our understanding of the relationship between the crystallite CTE and the bulk CTE underpins theories of dimensional change and models of irradiation-induced creep. By combining the data from these three series of experiments, we'll begin to build a coherent picture of how the structure and property changes caused by elevated temperature and irradiation in graphite at the nano and the microscale influence the macroscale response of graphite core components. Thank you very much for watching my pitch.